Hi everyone, second time. We met yesterday. We saw each other yesterday. The topic of the presentation today is validation and utilization of physics-based simulated ground motions for bridge performance assessment. It's the work that we started some time ago with Mesa at Beirut, but COVID-19 and a hiccup in our lab resulted in the project to be a little bit delayed, but we have a lot of stuff to show you. I changed the presentation and added some of the stuff that we had done in a past 10, 15 years on validating simulated ground motions. I thought that once people are bringing out their Gustav guns, and if you don't know what it is, you can Google it. We have been very slowly working on this validation exercises since 2008. And I'm going to show you some stuff as we go forward. So as always, acknowledging Pierre. And in this particular topic, Skek, who has been funding us and others who are in the room on validating simulated ground motions and in general for bridge work. Now, talking about my presentation today has a lot rooted in the past. I'm going to talk about why these simulated motions are needed, one slide, and then what are the types of the simulation, again, one slide, and then I'm going to go in depth in different ways that you can validate simulated ground motions and the arrows. So validation, and one of the things that we have heard yesterday and today is always forward-looking. Looking into doing performance assessment, and this can be for the bridge network at the regional level. You can also bring in simulated ground motions for earthquake early warning preparedness. And there are folks in England who have done some work that is related to this. They're still not there yet, but it is somewhere that folks who are looking for ideas for proposals, here we go. But you can use simulated ground motions to pad parts of the database of recorded ground motions, or even come up with an entire database of simulated ground motions that can be used for engineering work. And I know Jack and Greg, to some extent, have done some work in this area. Now, moving forward, talking about different ways of simulating ground motions. What was discussed so far in the presentations yesterday and today is the source-based, again, referring back to the Gustav gun, bringing out heavy artillery to do the simulations. But there have been folks who have done the work in the past on site-based, which is mostly is all stochastic. Armin and coworkers, which we have not only used their simulations for bridge response assessment, which is what I showed yesterday in my presentation, but also their work and the parameters that they use for the simulation is utilized for the validation. And that is the topic of this research that I'm going to show you today. So again, this is a philosophical slide, talks about key issues in validation. So with the experience that we have since 2008, any validation should be independent of the simulation method to make it fair. And it can, and it maybe should depend on the engineering application. Let's say you want to use simulated ground motions for evaluating the performance of nuclear reactors. You are very much at the stiff side of the spectrum. You need to look into your high frequency range. Looking into tall buildings, although that you have some acceleration response that needs high frequency, but the displacements are heavily impacted by the low frequency range. And again, all of these are philosophical notes and probably obvious to everyone that you need to identify some key parameters that you should be used for validation, obtain best estimates, compare, and then judge if it's good, bad, or ugly. The key point here is what is the validation parameter and in what regime you are doing the validation. In that note, and again, I keep referring back to 2008, Before 2008, folks were validating simulated ground motions by comparing wiggles. So they see the velocity trace, and except for the work that Anderson at UNR did in 2005, who came up with a quantitative measure to validate simulated motions, I don't remember anybody else did anything in that. Now, once it comes to validations, we have kind of professed this to be a work can be divided into three types: a type 1, type 2, type 3. Type 1, very simple. You have an earthquake that happened in the past. You want to see if you can replicate the same motions. It is a very simplistic view of the world. We did a lot of work here, which I'm going to show you a couple of slides. Type 3 is using simulations that happened in the past in the form of a database. As you can see, it is response condition on intensity measure. And Greg, Jack, and us, we did some work in this area. But the jewel of this validation happens in the middle, type 2, which is all about the trends. You are learning things from past earthquakes, and we know that what we have learned in the past is not complete, but that's all we have. And you want to predict what's going to happen in the future. And you need to make these small leaps of faith. You're entering in zones that previous earthquakes did not cover, but with having good models, you're hoping that the simulations can get there. But you need to take the steps very slowly, because we're getting into the norm of extrapolation rather than interpolation. And extrapolation is always a leap of faith, especially if you go far away from the zone that you have the data points. You might fall and break a leg. Anyway, type 1, this is, and I'm going to zoom through these. The references are here. I'm sure that the videos will be available for you to see in the, later. And this is the work that we did with Carmina, that he is at UCL London right now. We looked at Northridge, Loma Prieta. These are type 1 old earthquakes, applied it to SDOFs, different kind, and came up with the plots of this form: ratio of mean response from simulated to recorded. I want you to focus on these two zones. This is the ratio of sigmas. Ratio of simulated sigma to recorded sigma is small. That means simulations do not have that much of variation that the recordings have. I'm going to show you results later on from our recent work that this still continues. And this work was done, it was published in 2010, 11, and it's still going on. And the ratio of simulation to recordings is more than 1. That means simulations overestimate in average. Now, we also did the work for MUF structures, and still you see that the ratio of simulation to recorded average is more than 1, and the ratio of sigma simulated to recorded is less than 1. More intensity, less variation. We also did the work for bridges, and this is a picture of a 2010 publication that we had. We looked into two types of bridges, single column and two column, two span, both of them. And we looked into different skew angles. And consistently, we saw that averages in this particular case came out to be okay, maybe because it was the bridge had low period, but the variances are high. And the EDP that we're looking at is the column drift ratio and the rotation of the deck. Now with this, we enter the type 3 validation that we did. And again, Jack and Greg have done much more than what we have done in this particular regard. And we looked into the difference between the pulsiness of these ground motions. Although that this is for building, we didn't have money to do anything else, but we delivered something to the simulators that they later on fixed, and the simulations that happened after this work was less pulsy. With all of that, we looked back into the work that Armin and co-workers, in this particular case, we used Sanaz Rezaian's input a lot. And we looked into how they simulate stochastic ground motions. They are using some basic parameters like duration, areas intensity. T-mid, which I'm going to again explain all of these parameters and more to get to the simulations. We thought we cannot get into validating on the wiggle to wiggle because wiggles are relatively meaningless for our engineering work. But there is a subset of parameters that can be used as a vector that once validation happens at that level, you can be sure that your work is okay to do response assessment. The key thing is at what regime you are doing that validation and for what type of structure you're doing that validation. So two questions came to mind that we wrote this proposal. Can we develop an application flavored validation test for physics-based simulated ground motions? Which the answer is yes. And can we use physics-based simulated ground motions to performance assessment of ordinary bridges? And the answer to this one is almost yes. Depends on if you like what I show you today or not. So now this is the result of the work that we're doing right now. There is a process. I want you to think about a process of a ground motion generated. Nature gives you a ground motion, has a magnitude to the location that you are, has a distance, you have a VS30 at the site, and a bunch of other parameters. There is a motion that comes in. You can juice this motion from acceleration time to areas intensity and different these intermediate intensity measures, if you may. But these are the intensity measures that Armin and coworkers use for simulations. We are bringing them here for validation. And eventually the EDP, which is what we call Rod 50 CDR, which is equivalent to Rod 50 SA, is the response of the bridge in terms of the response of the column of a bridge in terms of drift, but at the 50 percentile. The same way that you get SA 50, Rod 50 SA, you get Rod 50 CDR. We're doing a comparison with the blue, the regression on the blue level. We're trying to find out what are the minimum set of those RZZ parameters that can describe the EDP. This is the efficiency part. We also do a regression between event parameters and the EDP. Combination of these two will show if the RZZs are efficient and sufficient. Once you have this set, you can only focus on the green regression. And if there is similarity between simulations and reporting at the green level, you can say that the ground motion is valid. Now, in this project, the regime that we're doing the work is not for a single ground motion, is not for a condition on an intensity measure. It's conditioned on 100 years of ground motion that happened in Southern California. In other words, we know that there is uncertainty in simulation. And going back to what David mentioned, that he is hearing from Norm that they need to do multiple simulations, this kind of relates to that advice. For 100 years of ground motions in Southern California, we're trying to generate simulations, many simulations. And then we have that one recording. If we can show that that one recording is a member of the population of the simulations, that is how we say that the ground motion simulation method is valid. And then the similarity is if the recorded coefficients for these regression equations fall into the 2575 range. If not, at least it is in the 595 range. If it's really falling outside, we are saying that this ground motion simulation method is not very good. Now, we are adding something to this. This is not the end of the story, and that's why the project is continuing. We are adding another form of regression to the entire mix that we're trying to kind of dovetail the two methods that later on, once we do our report, we can see everything together in one setting. Now, moving forward, I'm going to talk a little bit about what we did. We looked into Southern California. We looked into the eight ground motions that were relatively heavy down there, actually down here. You guys are up north. And we generated, and I'm going to zoom through these, we generated 100 simulated catalogs that are equivalent to the recorded set. These catalogs of earthquakes for Southern California have the same distribution of magnitude, similar distribution to the magnitude, not same, similar distribution of magnitude, and similar distribution of R-UP. So we want to show if this recorded set can be one of the simulated sets. So moving forward, taking our bridges, we have 4 bridges in this project, 3 of them are done. Applying the ground motions and rotating the ground motions and taking the central median value coming out of 10 rotations. And this is the total number of time history analysis that we have done. And we got the EDPs. Let's talk about those RZ parameters for a little bit. Everybody has been talking about duration, so we leave the duration as is. This is the acceleration trace. You can get the area's intensity by integral of a square. Now, the bottom here is the cumulative number of zero-level up crossing. That means anytime that we went up on the acceleration, one number gets added. The slope, if you can talk about TMID, the slope of this plot is a representative, a surrogate for frequency content. And the slope of that slope, that means variation of the slope along time, is the changes in the frequency content. And there's another parameter, what is called damping, but it's not damping. It shows the bandwidth of the ground motion. It's called epsilon, but in the spirit of brevity and making sure that I'm using the time efficiently, I'm not going to show it here. Now, we reduced the RZZs to what is important to estimate EDP. We used random forest method using the Barutha algorithm that we orders these RZZs for major and minor component. Anyone that gets a rate of 1 or 2 comes in. Then we do a variance variance inflation factor to find out if there is any collinearity between these parameters. And there is definitely collinearity between area's intensity in the major and minor direction of the ground motion. Removing that, we have the set of the RZZ parameters. Now with that, area's intensity of the major direction, duration of the major direction, duration in the 595 cents. F mid of major and minor direction means the frequency content of the 2 directions, and bandwidth of the major component are the parameters that are important for validation of simulated ground motions for OSB ordinary standard bridges. So moving forward, we form these equations. This is an equation that takes you from response, actually takes you from RZZs to response. The dot is the result of the regression from the recorded set. The ranges are the results of the coefficients from fitting the equation for the simulated sets catalogs. And as you can see, there is good, well, you can call it good. The recorded falls somewhere okay. And we are off, I'm sorry, went way too fast. We are off in B3 and B4, but we did further analysis and realized that although that F mid is important, but the importance is not as large as these 3, as B1 and B2, that is area's intensity and duration. Now, we fit ROD 50 CDR to event parameters. Now, in event parameters, this is trying to show that the RZZs are also sufficient. Again, a lot of good comparison between the coefficients, but there are things that are missing. The mismatch in basin and hypercentral responses. See the equations for C18, C16, I think, no, C14 and C11 are not good. And this shows itself once you come and do the regression of the RZZ versus events. The same parameters are showing mismatch, which basically shows that the simulations can improve in this range. What shows to be insufficient? Here, that is event parameters to RZZ show to be insufficient from event parameters to EDP. Last slide. We have a comprehensive methodology for almost validating simulated ground motions. Application is demonstrated for cybershake simulation motions, but you can do this for any other simulation method that you have. Is based on 3 transformations from event parameters to EDP, event parameters to RZZ-S, which is the subset of the RZZs, what is important, and RZZ to EDP. Since it is observed that the mean relations for RZS to EDP are consistent and explanatory, it is proposed that RZZ-S be the first step of future validation exercises. With that and a picture of this beautiful movie in the 50s, I'm gonna stop my presentation. Thanks for listening to me.
Great. Do you have any questions?
It was either crystal clear or it was crystal clear.
Can you tell us really quickly about your next steps in this project, please?
We are doing another form of regression. We are combining the recorded set and each simulation set into one setting and add a indicator element to that data point. It will get an I of 1, let's say, if it's simulated, and an I of 0 if it's recorded. If we can show that I is irrelevant, in other words, the significance level of that I is not too high for showing difference in the estimation of the response, that is another way that we can show there is similarity between valid simulations and the record. And from this point forward, I think that we are almost done with the thinking of for this project. What is left to be done is to take all of this work and put on the heavy simulation Gustav Gunn that folks have at Dave has at the National Lab, and we can basically do much better than what we did, because our technology for the simulation is the simulations of 2014-15 is CyberShake 12.14, I guess. I forgot the number, but it is a relatively old simulation at this point. New simulations have come out, new stuff, so probably the whole thing can be redone. But all the routines are there. We just need to push the data in and get some meaningful results out.
Great, thank you so much.